Hello and welcome to this debut edition of The Gradient. I'm your host, Krish. Today, we're taking a deep and perhaps slightly philosophical journey through the landscape of modern artificial intelligence. We'll start with the tools that are already reshaping our world: large language models and generative AI. Then we'll push beyond that horizon to the tantalizing debated concept of artificial general intelligence, or AGI. And finally, we'll explore what might lie beyond even AGI: the idea of world models, machines that don't just process data but might in some way understand their surroundings. This isn't just a technical discussion, it's about the foundational ideas competing to define our future. We'll conclude by weighing the perspectives of three pivotal, often clashing voices: Meta's Yann LeCun, DeepMind's Demis Hassabis, and xAI's Elon Musk. By the end, I hope to give you not just a summary, but a framework to follow this unprecedented technological evolution. So, let's begin with the present, the state of AI as it stands today. If you've used ChatGPT, asked a coding assistant for help, or been amazed by a photorealistic image generated from a text prompt, you've directly interacted with the current paradigm. We are living in the age of the large model. The engine of this revolution is a combination of the transformer architecture, unprecedented scale in compute and data, and self-supervised learning. Let's break that down. First, the transformer. Invented in 2017 in the landmark paper "Attention is All You Need," it gave us the mechanism of attention. In simple terms, it allows a model to weigh the importance of every word in a sentence relative to every other word, no matter the distance. This was a quantum leap over previous recurrent neural networks for understanding context and long-range dependencies in language. Second, scale. The hypothesis, vividly demonstrated by OpenAI and others, is breathtakingly simple. As you increase the size of the model, its parameters, the amount of training data, and the computational power used for training, its capabilities improve, often in unpredictable, emergent ways. We've moved from millions to hundreds of billions of parameters in just a few years. GPT-4, Claude 3, Gemini Ultra, these are not just programs, they are vast statistical representations of a significant slice of human text and code. Third, the training method, self-supervised learning. Unlike old AI that needed millions of painstakingly labeled images, this is a cat. These models learn by predicting missing pieces. For text, it's the next token prediction task. Given a sequence of words, what word comes next? By doing this over trillions of words scraped from the internet, the model builds an incredibly rich, multi-layered statistical map of language, concepts, and even reasoning patterns. The capabilities are staggering. Proficiency in language is the most obvious: translation, summarization, conversation, writing in any style. Code generation has made developers vastly more productive. Multimodality, where a single model can process text, images, and soon audio and video, is breaking down barriers between types of information. In specialized domains, AlphaFold solved a 50-year grand challenge in biology by predicting protein structures, and AI is accelerating material science and drug discovery. It feels like a charm, but it's crucial to understand what this magic is and what it isn't. Let's look at the fundamental limitations, the cracks in the foundation. This is where we separate the hype from the mechanistic reality. Today's large models are autoregressive predictors. They are phenomenal pattern matchers and interpolators within their training distribution, but they lack these traits: true understanding. They have no grounded model of reality. They don't know that water is wet, that objects fall when dropped, or that if John is in London, he isn't simultaneously in Paris. They can parrot the fact from their training data, but they don't possess the underlying physical or common sense model, reliability, and truthfulness. They are prone to confabulation, making things up with extreme confidence. This isn't a bug, it's a feature of their design. They are optimized for plausible sounding output, not verifiable truth. There's no internal truth checker. Reasoning and planning. They struggle with complex multi-step reasoning that requires holding and manipulating state or planning actions in a dynamic environment. They can solve a written logic puzzle from their training corpus, but cannot plan a real-world sequence of actions to achieve a novel goal. Causal understanding. They capture correlation, not causation. They know that thunder and lightning are often mentioned together, but they don't understand that lightning causes thunder. As AI researcher Melanie Mitchell puts it, they are stochastic parrots, incredibly sophisticated ones, but parrots nonetheless. They rearrange and recombine the patterns they've seen. This leads to a critical realization. Scaling current models bigger might get us better parrots, but it may not get us true intelligence. The output may become smoother, more useful, and harder to distinguish from human text, but the underlying architecture may hit a ceiling in terms of true reasoning, safety, and real-world agency. Which brings us to the trillion-dollar question. If this isn't the path to human-like intelligence, what is? This leads us to our next frontier, the quest for AGI, Artificial General Intelligence, AGI. It's a term that's lost some precision through overuse, but its core idea is powerful. A machine with the ability to understand, learn, and apply its intelligence to solve any problem that a human being can across a wide range of domains. It's not a super-powered chatbot. It's not just a tool for one task. An AGI would presumably possess flexibility, robust reasoning, common sense, and the ability to learn new skills from limited examples, the hallmarks of human and animal cognition. Why is today's AI not AGI? Because of the limitations we just discussed. An AGI couldn't confabulate. It would need to understand the physical and social world to operate safely within it. It would need to form and test hypotheses. So, what's missing? Many researchers point to a suite of cognitive ingredients that large language models lack: embodiment and interaction. Humans learn by acting in the world, touching, pushing, dropping, seeing, cause and effect. Our intelligence is deeply tied to being physical agents. Some argue that true intelligence can't emerge from text alone. It requires sensory motor experience, internal world modeling. This is the big one, and we'll dive deeper into it. An AGI would likely need a rich internal simulation of how the world works, a world model to predict outcomes, plan, and reason about unseen situations. Objective-driven behavior. Current LLMs have a simple objective: predict the next token. An AGI would have complex hierarchical goals. It would need to plan a sequence of actions to achieve an objective, constantly checking its world model to see if it's on track. Episodic memory and continuous learning. Humans learn continuously from a stream of experience, remembering specific events. Today's models are statically trained in one giant batch. They don't learn from new interactions in real time without catastrophic forgetting. The dominant debate right now is between two camps, often simplified as the scalers and the architects. The scalers, a view often associated with OpenAI's earlier philosophy and some at Google, believe that we are on the right path. They argue that with enough scale, more parameters, more diverse data, especially video and interactive data, and more compute, the current transformer-based architectures will develop enough latent world understanding and reasoning to cross into AGI-like capabilities. They see the emergent abilities as evidence of this. For them, the priority is engineering, bigger, faster, more efficient. The architects, championed fiercely by Jan LeCun, believe this is a dead end. They argue that next token prediction, no matter how scaled, is an insufficient objective to yield true understanding or reliable reasoning. They contend we need a fundamental architectural breakthrough, a new paradigm for machine intelligence. This camp is looking beyond scaling to a redesign of AI's core, and that redesign hinges on one compelling concept: the world model. A world model is an internal representation, a kind of mental simulator that allows an agent to predict the future state of its environment. Think about it. If you're about to place a glass near the edge of a table, your internal world model predicts it will fall. You don't need to try it and see. You can imagine the outcome of actions without taking them. Thank you for listening so far. If you like it, hit the like button, share the podcast, and subscribe to the Frontier AI channel. It will motivate me for my next podcast. Let's continue. For an AI, a world model is the key to moving from reactive pattern matching to active understanding and planning. Instead of just responding to a prompt, an AI with a world model could plan. To get the apple from the high shelf, I need to find a stool, place it stably under the shelf, climb on it, and then reach. Reason about counterfactuals. If I had turned left instead of right, where would I be now? Learn efficiently from few examples. By understanding the underlying physics or rules of a situation, it can generalize to novel scenarios. Jan LeCun's proposed architecture, which he calls a Joint Embedding Predictive Architecture, JEPA, is a blueprint for this. It's a modular hierarchical system where one key component learns to predict the state of the world in a latent, abstract space, not in pixel or token space. Other modules handle perception, action, and short-term memory. The system is trained to learn by watching hours of video, not by predicting the next word, building its world model through observation. This is radically different from LLM training. The goal isn't to generate the most likely next pixel or word, but to create a compact, efficient representation that captures the world's predictable dynamics. The AI learns what changes and what stays the same when an action is taken. If LLMs are like encyclopedic oracles, an AI with a world model would be more like a scientist or an engineer, able to propose experiments, imagine outcomes, and test its understanding against reality. This brings us to the precipice of the biggest questions. If we succeed in building AGI with robust world models, what then? And who is guiding us toward this future? Let's hear from the guides, or perhaps the prophets of this new age. The future of AI isn't being shaped by anonymous forces. It's being actively steered by the visions of a handful of influential thinkers. Their disagreements define the battlefield of ideas. Let's synthesize three of the most prominent voices. 1. Jan LeCun, the architect of cautious optimism. LeCun, ex-chief AI scientist at Meta and a Turing Award winner, is the most articulate critic of the LLM path to AGI. His view is a core thread we've already followed. On LLMs, he calls them ephemeral, unreliable, and inherently unsafe because they lack objective truth-seeking. They are, in his view, a diversion. On the path to AGI, he is a staunch architect. We need new, objective-driven AI architectures based on world models. He advocates for open-source development to ensure the technology benefits everyone and is not controlled by a few corporations. On risk and timeline, He is famously skeptical of existential risk from AI, calling it premature and a distraction. He believes human-level AI is still decades away and that the real risk is in who controls it and how it's used, not in it spontaneously becoming malevolent. His is a voice of scientific caution against both hype and doomerism. Next up, Demis Hassabis, the games master turned generalist. The CEO of Google DeepMind comes from a different tradition, using games as a testing ground for general algorithms. AlphaGo, AlphaStar, AlphaFold are his trophies. On LLMs, he sees them as powerful, transformative tools, but not the endpoint. At the 2023 AI Safety Summit, he called LLMs a key ingredient in the larger recipe for AGI. On the path to AGI, Hassabis is a synthesizer. He believes in combining the strengths of large-scale learning, like LLMs, with the algorithmic breakthroughs from reinforcement learning and simulation, like AlphaGo's tree search. His vision likely involves LLMs for knowledge and language, paired with planning systems, simulators, and reinforcement learning agents that can act and learn from interaction. He's betting on a hybrid, engineering-focused path. On risk and timeline, he is a leading voice on AI safety and alignment. He has stated that AGI could arrive within a decade and that its development must be paired with profound safety research. He represents the view that the technology is immensely powerful and must be steered carefully, with its risks taken seriously from the start. 3. Elon Musk, the accelerationist alarmist, a co-founder of OpenAI who left over disagreements on speed and safety. Musk is a bundle of contradictions, both driving AI forward with XAI, Grok, and warning it could destroy humanity. On LLMs, he uses them in Grok, competes with them, but seems to view them as both a stepping stone and a potential hazard if not aligned. On the path to AGI, he is a hardcore accelerationist in practice, building massive GPU clusters and chasing scale, but a doomsayer in rhetoric. His stated fear is that AGI will surpass human intelligence so rapidly that we will lose control. He has called it the biggest existential threat and likened it to summoning a demon. On risk and timeline, he is the most publicly apocalyptic, suggesting AGI could arrive by 2029 and poses a 20% risk of destroying humanity. His solution is paradoxical: race to build it first with XAI to ensure it's truth-seeking and hopefully benign, while simultaneously calling for regulatory pauses. His stance is one of prophetic urgency and deep conflict. Where does this leave us? Listening to these three is like hearing three different stories about the same event. LeCun is the engineer, focused on the blueprint, convinced we're building the foundation wrong. Hassabis is the strategist, assembling proven components into a winning whole, mindful of the game's stakes. Musk is the prophet opportunist, sounding the alarm from the temple steps while also selling tools from his own workshop. Personally, I find myself leaning toward a synthesis of LeCun and Hassabis. I believe LeCun is fundamentally correct about the architectural ceiling of pure LLMs. True understanding, reasoning, and safe real-world agency will require something like world models and objective-driven design. We cannot simply scale our way to safe AGI. However, I don't think the LLM path is a total diversion, as LeCun sometimes suggests. Hassabis's hybrid approach feels pragmatic. LLMs, for all their flaws, have given us an astonishing knowledge compression and interface layer. They are a phenomenal tool for accessing and manipulating the world's information. The future architecture may well use an LLM-like module as a high-level planner and communicator, grounded by a lower-level world model and a physical or simulated action layer. As for risks, I side with Hassabis's proactive safety over Musk's apocalyptic panic or LeCun's dismissal. The risk isn't a sci-fi robot rebellion. The more pressing dangers are massive structural unemployment during the transition, unprecedented concentration of power in the hands of a few tech giants, supercharged disinformation, and the catastrophic misuse of powerful AI systems for cyber warfare, autonomous weapons, or bioengineering. These are complex societal and political challenges that demand our immediate attention, not just futuristic speculation. The most likely near-term future is not a sudden AGI explosion, but a gradual proliferation of increasingly capable, specialized AI agents, powered by improving world models that automate vast swaths of science, engineering, and logistics. The transition will be chaotic, economically disruptive, and geopolitically tense. Our task is not just to build smarter machines, but to build wiser societies that can harness this power for collective flourishing while mitigating its immense dangers. From the pattern-matching power of today's AI through the conceptual leap to AGI and world models to the clashing visions of its foremost architects, it's clear we are not just witnessing a technological change, but participating in a redefinition of intelligence itself. The gradient we're climbing is steep, and the map is still being drawn. The only certainty is that the choices we make about how to build this intelligence and for whom will echo through centuries. Thank you for joining me on The Gradient. I'm Krish. If you have thoughts on this journey, I'd love to hear from you. Until next time, think deeply.